Hi, everyone. Thanks for joining. Welcome to day 3 of Intro to Data Science with Lambda School. You've learned now some about Python, and you've learned some about the Python ecosystem, about how to import libraries and use them like pandas. This is great because in general, what makes computers so powerful is that we don't have to do everything from scratch, right? We can build on the work of others. That's a very powerful thing. It's not as easy as just saying, oh, and I will build on the work of others. You have to understand a bit about the work of others to do it successfully. But it's worth it, and it's very powerful. So I'm going to start by sharing my screen and answering a few questions, and then I'm just going to get right into it. The flow is the same as previous days at this point, so I'm not going to spend a lot of time on it. If you have questions about process, where there's a link to a form, what you should be filling out or doing, ask, and a PM will help. All right, everybody see my screen okay? So I'll start by answering some questions here. Will the instructor typically be sharing the lecture notes? Well, typically, yes. And I will share these lecture notes right now. Now, I will also be running through them in front of you. So for the next hour, I suggest you focus your attention on that. But they are here for your reference. And in general, if you go up here, the place with all the links to all the other places, aka the training kit, it should have links even to, I believe, the material from last night. So Ryan was live coding, right? It's a sort of fun, more interactive style of teaching, perhaps. But he does have the actual typed notes, and I believe this link is essentially very similar to all the things that he showed you. So you have that available as well. You just have to click through to get to it. And there will be a lesson 3 assignment, but let's start with the lesson first. And it should all be on learn.lambda school as well. If it's not, we'll get it there shortly. So what's the topic tonight? Statistics. Okay, now we're gonna have to grin and bear it and do some math a little bit more directly. It's not too scary though, I promise. I'll start with a joke even to lighten the mood. 3 statisticians go hunting and they see a duck. And the first statistician shoots and misses to the right. The second shoots, misses to the left. The third shouts, "We got it!" So, statistics joke, right? It's making light fun of the sort of, well, I don't know. I won't defend it. These jokes are cheesy, right? But exactly. Boom. Save that one for whatever fancy cocktail parties you go to with statisticians, except they probably all know it. So what is statistics? It's the mathematics of organizing, analyzing, and interpreting data. Well, gee, that sounds familiar. That sounds important. Really, it's the foundation of a lot of what we're doing as data scientists. And it's a pure, I put this in quotes, a pure abstract math topic. What does that mean? Well, it means it's math. It's something that a math department might care about, like calculus and trigonometry and analysis and combinatorics and so forth and so on. It is math. But somewhat unlike most math, it can be pretty directly applied to real-world situations because it is actually the math of error and uncertainty. The reason, exactly, statistics is about being inexact, perhaps. That's a good way to, now it doesn't mean it's up for interpretation necessarily. And this, I won't go too far. It's a philosophical tangent. Just because statistics has error to it doesn't mean that, oh, nobody really knows anything and everybody's making it up. No, that is not the case. There might be some places where people are making things up, but we don't need to worry about that. That's not what we're doing. Really, the reason we need statistics is because it's not possible to collect all the data ever. That's why, right? The pure math solution to things involves these concepts like infinity and it involves having exact, perfect, complete information. And if we try to do that in the real world, that's what we call a census. And you might have heard of that. That's what the US tries to do every 10 years. None of the founding fathers were statisticians, unfortunately. And the census is expensive. And the US kind of pulls it off, but certainly it's not something everybody can do all the time. It's generally expensive and unrealistic to, like, if you let's say you ran a marketing company and you wanted to know how people thought about your latest campaign, and you know that, oh, we bought advertisements and it was seen by 20 million people. Are you going to chase all 20 million of those people down, right, and ask them all questions and figure out what they thought? No, you're not going to do that. You're going to get a sample, a subset of the people, and then we can use statistics to say things about the broader population, all the data that the sample is supposed to represent. So if you've ever received a phone call asking you questions about your opinions about things, that was some company that was trying to collect a sample of people by randomly dialing phone numbers and then ask them questions and say things, right? So there are two types of methods in statistics: descriptive and inferential. Descriptive is summarizing data with measures you may have heard of, like the mean, median, and mode. That's a lot of what we'll be doing today. In fact, that's what we'll be doing today. We'll talk a little bit also, though, about random variables and distributions. So we'll be a little bit more quantitative about these topics than maybe you've been in the past. Inferential statistics is really cool. We will not be talking about it today, but it means identifying patterns in your data and then making predictions. So you have a sample, you identify all these patterns in it, and based on that, you can actually predict things about stuff you haven't seen yet. And that's pretty clearly powerful. So that said, it makes more sense to start descriptive. So here we are. Before we get any further, any questions on my prologue here? People motivated to learn some statistics? Let's do it. All right. So just reinforcing a little bit, probably not super deep, but I love Bayesian statistics. And yes, I will almost certainly end up talking about it at some point in those 30 weeks. We will not talk about it today because we don't have much time, but it's a great topic. People curious, start with Wikipedia. So to really reinforce what we're talking about here, the foundation of statistics is this thing called random variables. And you might have already, well, I know what a variable is, right? I did algebra. I wrote some programming stuff. There are variables there, right? Yes, those are variables, but in most of math, when we just call something a variable, that's a symbol for something that is arbitrary and perhaps even unspecified or unknown, but in some sense, unchanging and unique. It is still some singular value. We don't know what it is, perhaps, or we have to figure it out, but it's one thing anyway. And so look at this. What is y? Anybody? I have a little bit of math here. It's a tiny bit. What's y? X equals 2, y equals 3 times x, y equals 6. Yes. I know that sometimes it seems like I ask simple questions. It's still good to answer because these really do connect to the concepts, okay? And this is about exercising your brain and connecting things you do know, things like you're comfortable with this, right? You can figure this out, connecting this to other things. So in this case, I'm actually kind of drawing this out as like, this is not a random variable. This is a variable you're familiar with. So it's important to know a random variable is something different. A random variable in statistics is usually written with this capital X here, if you're doing it in a proper math context, and is a variable that ranges over some possible values, and essentially these reflect the outcomes of what you could call a random process or phenomenon. So a good simple example that probably most of you are familiar with is you could roll a 6-sided dice, right? And if you roll a 6-sided dice, what could happen? Before I scroll, let me just show the picture here. What's something that can happen? I roll a 6-sided dice, I look at the top, what do I see? Sure, I see 1. I see anything from the interval 1 to 6. Sure. I'm never going to see a 7. I'm never going to see a 0. Never going to see 1.5 or pi. I'm just going to see one of these numbers. What's the chance that I'll see the number 4? Yes. What's the chance that I'll see the number 2? Yeah, you can keep just saying 1/6, right? It's the same for all of it, assuming, of course, a fair dice. So that's essentially what I say down here, right? Assuming it's fair, there are 6 outcomes, and we can just enumerate them. This is like a Python list. Hey, our friend, the Python list. Yes, there's a reason for that. And we're going to say they're each equally likely. So this is the one time I'll sort of write it down with math and not code. If we wanted to describe this with math syntax, we would say something like the probability that capital X, our random variable from our that we're drawing, is equal to little x, any particular x, is equal to 1/6 for x in 1 through 6. And that's what this weird little e thing means, contained in, essentially, or is inside. In any case, if that looks like Greek to you, well, it's because it is. And you don't necessarily have to worry about it, but it's gentle Greek. And this is how the math people talk about these things. So it's good to look at it a little bit. But we're data scientists, so we're going to write some code. All right. Feel free to ask questions or make further comments. I'll keep going for now, just to keep on top of things. So there's different sorts of random variables. The first sort of one we're going to look at is discrete. These take values from an enumerated set, just like the dice example above. And so it means that it's one of some. And enumerated means you can count them. You can put them in a list. You can just sort of say these are the options. So the rule for a discrete random variable is that the sum of all the probabilities, so each of these options has some probability. In our case, it's each a 6th. The sum of it across all the options has to be exactly 1. That checks out here. We've got 6 options. They're each a 6th chance. Add that up, you get 1. Let's reproduce this in Python. We're going to start with a handy thing in the standard Python library called random. Oh, it's spinning up the instance for the first time. There it goes. And what I did here is I imported it, and then I used a function I use all the time in a Python REPL, which is called dir. And dir lets you look inside something and tell you sort of what lives there. The computer science term for what's going on is we're looking at the scope of what's in the namespace or something of this object. And if you don't, it's what lives there. That's all we're really saying. And so what lives inside random? Well, all sorts of stuff. And this is kind of overwhelming. So this is scary. I'm not asking you to understand this, but the little underscores usually indicate things you should not worry about so much. Those are like internal Python things. You care about things that don't start with underscore. So we go down here and we're like, hey, there's this thing, rand int. Well, that sounds promising. Remember, what we want to do is reproduce a 6-sided dice. And a 6-sided dice, each roll is giving us what sort of number? What are the 2 sorts of numbers we can have in Python? Int and float. And what sort of number do we want right now if we want to simulate a dice? Int, exactly. So hey, rand int. Now I get to show you my other favorite little Python REPL function, help. So we're like, okay, we found this thing called rand int. The name sounds good, but the name's not enough for us to know what we're going to do. If you call help on anything, really, in Python, you get a little bit of help. And what does it say? Well, rand int takes an A and a B, and it's a method that lives in random.random, and it returns a random integer in the range A to B, including both endpoints. Perfect. That's exactly what we want. We want a random integer from the range 1 to 6, including both endpoints. Let's give it a try. Got a 3. And part of the reason I'm running the code live tonight is to show you what happens if I run this again. Anybody want to try to guess what we'll see? Are you feeling lucky? All right, we got a 4, we got a 2, a 5. Any number one is, I mean, yes, sure. Hey, we got a 2. And it's going to keep changing. It really is random. A 4, a 2. I mean, this is our little dice roller thing. If you're going to try to make a board game in Python, there you go, right? This is how you can roll dice. It's fairly nice and simple. But of course, it's kind of tedious to rerun this block of code to roll the dice. So let's use Python lists. Python lists and Python list comprehensions let us do a whole bunch of things. Now, there's another little bit of Python convention I'm mixing in here. So this is a list comprehension. We have a for loop at the end of the list, and then whatever's happening in this loop, we are doing this each time and putting all those results in a single list. But what's this underscore about? Well, this underscore is because I actually don't care about the value from range. I don't need it. I'm doing the same thing. Every single time I'm calling random.randint16. That's what I'm doing. And because I don't care, like you could say, oh, I should say put for I or for X or for N, or you make up some name. That name doesn't mean anything. You're not using it over here. So for underscore is a convention for saying like, okay, for this many times. Let's take a look. And there we go. A list with just a whole bunch of dice rolls. And now if you run it again, a whole bunch of different dice rolls. That's great. All right, well, what can we do about this? Well, there's one thing we can do. We can figure out the mean. The mean is the first and one of the most important statistics for you to know. The mean is just the total of all the values divided by the number of values. You probably already know this, but it's good to sort of formally think about it. And just to prove that this works and that this is random, let's run it again. We have different die rolls. Run this again. Different number here, 3.8 instead of 3.32. So it is random, but it's about the same. We'll might come back to talking about that a little bit. Another thing we can do is we can figure out the median. So this might look a little bit intimidating, but let's break it down. Does anybody know what the median is? How do you intuitively define the median? Yep, the middle number, and exactly, you want to sort it, because if the list is in random order, the middle number is essentially random. That's useless. But if you put them in order, the middle number sort of tells you something about where the center of the distribution is. And there's a handy Python built in called sorted, which takes a list and returns it, but in order. And then of that list, I'm going to take, well, its length is how many items are in it, but I'm going to divide that by 2 to pick out the middle element. And I get 4, evidently. That's interesting. Sometimes when I run this, I think I get 3. Let's find out. Yeah, I got 3 this time. I feel like 3 might be more likely, but I'm not sure. In any case, yes, if there's an even, this is a little bit sloppy, right? There's actually 100 items, so we should be averaging the 2 middle items. It's the middle item when you have an odd number of items. When it's an even, so let's rerun it with an odd number of items just to be correct here. So that really is the median. When it's an even number of items, there are built-ins. I'm just showing it to you because writing it yourself is how you can understand how it works. There are built-ins, of course. Anyway, as I was saying, if there is no single middle item, if there are 2 items in the middle, you can average them and like mean them, that is, add them up and divide them by 2. Now, I did this with sorted and not sort. And that's because sort will do this in place. And so if you sort it, you then have to look at the middle element as a second line of code. Anybody know why I put 2 slashes here, though? Yep. I don't want a float. I want an integer because this is supposed to be an index into a list. And indices into lists are always integers. So that gives us the same value, of course. I kind of prefer this one, so I'm going to leave it this way. All right. For your assignment, the mode, you might be figuring out a little bit about that at some point. But intuitively, what would we expect the mode to be? What is the mode? Anybody know the definition of the mode? That's the other main sort of measure of the most representative number of a bunch of numbers. Yeah, the most frequent number. So it's whatever number we see the most often. Now, what's that going to be? 7, yes. I don't know. I mean, we'd have to code it up, but exactly, it's not. There's no particular tendency. Each of these numbers is equally likely. So we'll always expect this to be around 3 or 4, and we'll always expect this to be around 3 or 4, because that's kind of halfway, right? And so for this sort of case, mean and median are interesting. Mode, actually not that interesting for this case, right? It's any number could be the mode just because it happened to be rolled a few more times. And that doesn't tell us anything about the distribution as a whole, really. Now, there are distributions where you might care more about the mode. Sure, you know what? Check, that's a good point. Perhaps the best way to check for an unfair dice, do this experiment a bunch of times, like roll it 100 times and then do that 10 times and check the mode each time. And if the mode is the same, that's an unfair dice, right? Because it's rolling some number way too often. All right. Any questions on discrete random variables? They're kind of friendly, intuitive. We've all rolled dice. We know what it's like. We're about to get a little bit more mathematical, though. All right, onwards. Continuous random variables. All right, now things get a little bit more philosophical. We'll see. So the other sort of random variable is continuous random variables. And instead of taking these specific discrete values, 1, 2, etc., they take any real value in an interval. And some of these distributions actually range over the entire real line from negative infinity to positive infinity. And at this point, I put an exclamation point here because we have to take a brief aside and understand what intervals are. I'll be efficient here. Maybe some of you already know about this, but you should be able to read this notation. So what this notation is talking about, this is different from when we were looking at Python lists, right? This is a bunch of numbers separated by parentheses and brackets. That's great. It's a Python list. But in a math context, and I try to make it clear with how I typeset it here, in a math context, instead, brackets are closed intervals, which perhaps kind of counterintuitively include the endpoints, and parentheses indicate open intervals, and those exclude the endpoints. So including the endpoints means that the random distribution could potentially draw any number from A through B, including both A and B. It could return those numbers. Those are in the distribution. Excluding something, like this case, means that B is like the upper limit, but you can never actually get B itself. And this would be a half open interval because it includes A on the left, but it doesn't include B on the right. This is the opposite of that, and then this is just an open interval. Any questions on that? Is this the first time let me do this as a poll. This is the first time I've seen interval notation. Yes, no. And I'll make it anonymous. This is just for our information and to best help you. So yeah, it's sure, since high school. Maybe you've seen this, but it was a long time ago in a galaxy far, far away. And that is why we are talking about it. That is fine. You might find you remember things. every now and again from high school or wherever. So why is this important? Well, it's because it's how we describe these things. It's how we talk about the range of the continuous variable. So let's see here. How can we talk about continuous distributions in Python? Let's skip to the Python code. I find code friendlier than math sometimes. Well, there's this thing random.random, and it returns an x in the interval 0, 1. And hey, it's using this notation that I just talked about. So what sort of interval is this? I just said it a moment ago. Is it closed, open, half closed, or half open? Yeah. I would call this a half open interval, or as I mean, maybe a mathematician knows the difference between half closed and half open. I would say they're the same thing. Exactly. The glass is half full from 0 to, but not through 1. And if you look around, a lot of programming languages have some random function that is exactly this, that returns just random numbers from 0 to 1. That might be the only random function they have, by the way. And if you want to get other distributions, you have to do logic to try to transform it. Python is friendlier to math, and Python gives you more distributions. You saw when we looked at everything that lived in here, there's all sorts of stuff. There's gamma, there's Gauss, there's log, norm, variate. Don't worry about it now, but the point is Python has you covered. But we're going to start with good old simple random, and let's run it. Exactly. It's like math.random in Java or JavaScript. And yeah, if we run it, what do we get? We get a number, and it's got a lot of decimal points, and it's just this. So this is I almost said it. What is this? What sort of thing is this in Python? A float. And by the way, you can ask that by printing the type. There's a built-in. So if you ever want to ask Python, hey, what sort of thing is this? Well, just tell Python, hey, what's the type of this? This is a float. Great, thanks, Python. Does the, where in the doc exactly? Oh, here. I think this, yeah, you could see this as, this is the executing the function, and this is the return of the function. So this is a programming language. So it's not, function isn't quite as pure as what math functions are. And this function in particular, these are empty parentheses because there's no arguments, right? It returns a number from 0 to 1. You don't have to feed it anything. The way we did with randint. In this, we just run it and it gives us a number. But yeah, I think you could think of it as input to output. I think might be the best way to think about it. Good question. So as with randint, I mean, it's a lot of fun to just run this line of code over and over, but really we're getting some high numbers here. But it's random. We get a low number now. It's nicer to run this a bunch of times at once with the power of lists. So we'll do that. This is exactly the same as the earlier list comprehension, just a different thing on the left. And let's look at what we get. Hey, yeah, we get a bunch of numbers, and they're all in this interval. Lovely. And look at this code. It's exactly the same code as what we did to calculate the mean before. Just add all the things up, divide it by the length of the things. And hey, the median, also exactly the same code, right? Put them in order and pick the thing halfway through. And again, I'm being a little bit sloppy here because there's an even number of things, but it's pretty close to the median. It's the median's, neighbor at the very least. So does it make sense to ask about the mode? What's the mode of all these random draws? Anybody have thoughts? Yeah, there is none. And the way I like to talk about it, as I wrote here, real numbers are soupy. What do I mean by that? Well, it means that there's a whole lot of them. And, We have to start talking about infinity. Well, we don't, but but there's always just numbers between numbers and numbers within numbers and more numbers. There's always numbers, and so every draw is going to be unique. That's the assumption from a continuous distribution. It's all going to be in this interval from A to B with whatever endpoints, but it's going to be unique. And because every draw is unique, yeah, I mean, either everything is the mode or nothing is the mode, or it just doesn't make sense. Oh, so just to explain better, it might be easier to type a smaller case here. What's the mode? I'll even put it in order. What's the mode of this list here? 1, 2, 3, 4. Sorry, not the mode, the median. I was just talking about the median. What's the median? Thank you. Brian answered what I was thinking. So you're psychic. Yes. How did you get 2.5? That's not in the list. Yeah, it's the middle. So the convention, if this was your list, you say, the median, that's easy. It's 2, right? It's in the middle of 1 and 3. There you go. In this case, well, wait a second. Is 2 in the middle or is 3 in the middle? They kind of both are because there's an even number of things. They're the 2 central elements. And so the convention is add them up and divide them by 2. And that gives you the true median in a case where there are an even number of elements. And so what I'm doing here is I'm not doing that. I'm just looking at the middle element. Now, that convention matters less and less the more numbers you have, right? We have 100 numbers. So if we fixed this, it wouldn't be that different. But sure, that might well do it. I will let people explore that on their own. All right. Now, we were just talking, though, about how mode doesn't make sense. Everybody clear on that? How every draw is unique. And when everybody is unique, nobody is, or something. Well, pandas and statistics are actually very good friends, as you'll see. So it doesn't make sense to talk about mode, but one thing that does make sense, let's go back to sort of put our Python hat on here, because we got to wear a lot of hats as data scientists. This line of code is basically exactly the same as this line of code, right? Our mean function. So let's put it in a function. Let's define a mean function. It sounds like a job for a function. Whenever you've got lines of code that are just the same thing, you're copy pasting the same code, running it over and over, that sounds like a job for a function. And what does numbers do? Well, it takes numbers and it returns the sum of them divided by the length. There you go. We wrote our own mean function. And as an exercise, consider trying to write median and mode functions. Now, you might have seen this by now. Sure. Yeah, you can get very mathy about these things. It's a good point. I'm not going to go into it. For practical intents and purposes, if you have an even number of elements, average it. And for really practical intents and purposes, you're going to have a whole lot of numbers, and just the one that's about halfway through is the mode, and that's okay. Sorry, the mode, the median. I keep on mixing those up. So discrete random variables had to add up to 1, right? Remember, we had 6 options, a sixth each. They added up to 1. Continuous random variables kind of do the same thing. You can say, yeah, they have to sum to 1. But as I just said, they're real numbers. They're soupy. You can't really add them up because there's an infinite number of them, and there's always more of them even between them. So you don't actually add to 1. You integrate to 1. Dun, 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 calculus. Now, don't worry. I just have a picture of calculus. We're not going to go through the details of calculus at this time, but this is one of the main ways that statistics and data science touches on calculus. The other way is when we start talking about some of the optimization techniques and trying to sort of find the gradient, the direction of a function. That's a lot like derivatives, right? But here, when we want to have a continuous distribution, it needs to integrate to 1. if that doesn't make sense to you, let me do another poll here. How much calculus, or comfort with calculus? Yeah, say comfort with calculus, 1 low, 5 high. Let's do that. And I'll make it anonymous again. So wherever you are, it's no. So pre-calculus is harder than calculus. I can never keep all the trigonometric identities straight. I always have to look those up. Wherever you are on this poll, it's okay. We're not going to ask you calculus questions. There are things about, I was talking about how with computers, we get to build on the work of others. Math does the same thing. Statistics is built on probability and calculus and set theory and these other topics. And so you'll see hints of them from time to time. And, it's good every now and then as you have time to look up whatever resources work for you, Khan Academy or like MIT OpenCourseware, and refresh these topics if you feel a little rusty on them. But right now, it's enough to just say, because this is continuous, we can't just add the numbers up. So instead, we have to use calculus, which is exactly the practice of dealing with situations like this, dealing with these little tiny infinitesimal things and somehow making sense of them. Sure. Calculus the easy way sounds good to me. I don't have strong opinions about, I don't think they're, at this point, I don't think it's about types of calculus. I just think essentially calculus 1 and 2 from a traditional like first year undergrad or perhaps AP sort of treatment, right? Like derivatives and integrals. You don't have to get too fancy, worried about analysis and multivariate stuff. You just need an intuition for what a derivative is and what an integral is, and to maybe kind of recognize them and solve easy ones, right? You do not need to be able to solve really crazy things or anything like that. And I wouldn't even call this a strict prerequisite for the full-time course, but it is a good thing to look at. I will say that. Any other questions on my scary calculus picture? Yeah, yeah. I've seen that. And I mean, to be honest, yeah, trig doesn't come up too much for us, in my experience at least. All right, onwards. Got to keep moving. I think we're on track tonight, though. So we've talked about random variables. That's the foundation, right? If you spend some time, again, go back up here and think, okay, these are variables, these are random variables. They're different. They go over a range. They're random. They truly have uncertainty baked into them. These things are not uncertain, right? They're arbitrary or unspecified, but they're not uncertain. These things are uncertain. And that's the foundation of statistics. Statistics is about understanding and characterizing these uncertain things. And the big ways to characterize it really is just mean, median, and mode, if I can keep them straight. So these random variables, you can describe basically any observable process this way, right? That's what makes this so powerful. And that's where we get to data science, really, is we can talk about all sorts of things as random variables. The number of times a dog let's see here, the number of times a dog smells something when it walks, I don't know. That could be a distribution of some sort. Probably not a very useful one. But the point is, that's that word, distribution. That's how we talk about a pattern of a random variable. And there are certain distributions that you see over and over again. The dog smelling distribution is probably pretty unusual, but these distributions are ones you see all the time. Now, there's a lot of them. I'm just going to highlight two: uniform and normal. If you want more, I mean, Wikipedia will lead the way, and a bunch of these things were other distributions. Gauss actually is another word for normal, as I'll discuss. And there's other distributions that you can find. But let's start with uniform. And guess what? Yeah, you don't worry too much about partial differential equations. They're cool. Don't worry about them, though. Um, if you have the wherewithal and time to study it, I don't mean to discourage you, but I don't see it as a prerequisite at all for anything we're doing. The uniform distribution. You've already seen this. A fair die is uniform. This is kind of the most intuitive distribution to us humans. That's why you were all able to naturally sort of say a sixth, right? You know the uniform distribution. It's in your head. You already know it. All it really means is a distribution where all the outcomes are equally likely, or if we want to be a little bit fancy, equiprobable. So it can be both discrete and continuous. You've seen discrete. That's the die rule situation. And you've seen continuous. That's random.random, right? That's why when we looked at the mean and the median, they were both kind of a half. And if we run this again, yeah, it's pretty close to a half, right? So, you know, it's kind of, it's evenly distributed from 0 to 1. So when you average it, you get halfway through. That's a uniform distribution. What real world data is uniform? Well, I've got a few cute scenarios here to think about. A raffle. If you sell 500 tickets to 500 different people, and then you draw one at random to pick the winner, that's a uniform distribution. It's also essentially a 500-sided dice, if you wish. You're at a bus stop, and a bus comes by once per hour, but you don't know when it was last through. You just know, okay, that it comes through once an hour. The time you'll have to wait for the bus to come through again is actually continuous, because time is continuous, right? Time is like a float. It can be arbitrarily specific, and it's unique. A continuous interval of 0 to 1 hours is how long you'll have to wait for the bus to come by again. And here's another one, another sort of discrete case. If you have 317 baseball players and you rank them all from their ability and you select one of them at random, their rank will be distributed uniformly over all the possible ranks. That makes sense. So exercise that I'm not going to do unless I get through this faster than I expect, but write code to express the, but let's do one of it. How do we write code for the raffle? Should be quick. I want a raffle draw. I want to pick a winner. I have tickets from 1 to 500. How do I do that? Yep. Random.rand int 1 500. Oh, and I guess I might need to tell it to print. All right, will the holder of ticket 226 please step forward and claim this fabulous flat screen television? Yep, exactly. You can try to work through these others as well and simulate them as you see fit. And it's okay to be a little creative if you want. Try to make a little scenario. Let's talk about the other big distribution out there, though, the one that's a little bit less intuitive. The last bit of really scary math I'm going to show you tonight, the normal distribution. So let's do this as one more poll. I've heard of bell curves. Yes, no. All right, so most of you have heard of them. Maybe if you haven't, that's okay. This is what they're talking about. It's the informal way to refer to this distribution. And why? Well, because it looks like a bell, I guess. It's shaped bell-like. It has this sort of meaty center, and then it thins a bit, and then really long, thin tails. It actually goes from, it's one of those distributions that goes from negative infinity to positive infinity. It approaches 0. It gets infinitely thin out there. So you never really draw it that far out, but it does. This distribution ranges all the way over the real line. And what is it? Well, as I said earlier, it's also called Gaussian, and that's because the formula for it was discovered by Carl Friedrich Gauss, a mathematician who did lots of this sort of stuff. And the formula is this. And I'm not going to ask you to memorize this. I'm just showing this to you for the sake of completeness. You can revisit this and try to memorize it later on. It's scary looking, and you don't need this formula, generally speaking, in most situations. You can look it up in most situations if you did. Usually, We're data scientists. We're going to use functions and code to do what we're talking about. But the formula aside, if we look at this, okay, it's got this nice curve to it, and there's different ones drawn here. That's because this distribution takes parameters, and the uniform took parameters too. What were the two parameters of the uniform distribution that sort of tell us what we need to know about the uniform? Because it's not enough to say, oh, I have a uniform distribution. You have to say, I have a uniform distribution. Yeah, exactly, the range. So exactly, from start to finish, from A to B. And I guess you might also want to say I have a discrete uniform distribution or a continuous uniform distribution, and then from A to B. And that tells you everything you need to know. Like that characterizes the distribution. The normal distribution is not characterized by the endpoints, because I just said it's infinite. And it's clearly a continuous distribution. There's no discrete normal. You can approximate it. We'll get to that. But it's characterized by, more Greek. What's this? Anybody? Mu, yes. And what's this one? Sigma, yes. Mu is how statisticians like talking about the sort of the center, the mean. Now, in this case, the mean and the median and the mode, what can we say about them? Well, I mean, not mode, sorry. It's continuous, no mode. But the mean and the median, what can we say about it? They're the same, symmetrical distribution. But what we're saying is it is centered at 0, and then sigma is its spread. That'll be talked about more tomorrow. There's a concept of variance and standard deviation. Don't have time to get through it fully today, I'm afraid, but you can think of it intuitively right now, how far apart these things are, how much spread they are. And you can see it, right? So this blue one, 3 of them are centered here at 0. The blue one, the red one, and the orange one, or yellow. And their only difference is sigma. Blue has the smallest sigma, red has a sigma in between, and yellow has a really big sigma. And so the yellow is really sort of big and wide, like a pancake. The blue one is really tall and skinny, and the red one is in between. The green one is over here. And why is the green one over here? Well, because its center is different, down at -2. But it's still symmetric around that center, and it still has its spread, which happens to be 0.5. So last question. Anybody know there's something special about this red one? What's the name for the red one? The normal distribution with mu equals 0 and sigma equals 1. And sigma squared equals 1, because 1 squared equals 1. This is the standard normal, exactly. And why is it standard? Well, we will get to that in just a second. So you might be thinking, like, all right, why are we looking at bell curves and talking a little bit about scary math? Well, why the normal keeps coming up. It keeps on showing up, and that's why we care. And it's used for hypotheses tests, something else you'll learn about more in the near future. And the reason is because, well, let's try to make it. I'm going to define a function here, roll dice. Roll dice returns a list that rolls the random integers from 1 to sides for the number of rolls. And I have some default parameters here, 6-sided dice, 100 rolls. So let's go ahead and play with our function. If we do it with the default arguments, well, we get a list of length 100 with a bunch of numbers from 1 to 6. Great, that's exactly what we expect. Let's play with it. Okay, 20-sided dice and 10 throws. Yeah, there we go, all right. 10 numbers, random numbers from 1 to 20. We run this again, get different numbers. Great. Now, we can use this to do something called the Monte Carlo method. I won't go into too much depth here, but it sounds fancy, like a hotel somewhere. It's really just a simulation. You simulate something by looping it over and over again and analyzing those results, and sort of making up your own experiment computationally. So I'm going to run 10 experiments, and I'm going to print the experiment I'm on, and I'm going to roll the dice, and I'm going to look at the average. Oh, hold on. Did I not execute the code block to define the mean function? Need to define this mean function because I'm using it, right? So I'm using our mean function. That's why we write functions, to reuse them. Okay, so we're running our experiment for experiment 0, because remember, we're on a computer, things start from 0. Our average is 3.51. Then our average is 3.41. Then it's 3.29, 3.3. Okay, yeah. Looks like it's always 3 point something. It's hard to tell from just 10 experiments. We can run another 10 experiments. But this is a computer. Why are we just running 10 experiments and looking at it? Right? We can run the experiments and save the results. So we'll make a list called means, and there's a question a lot like this. So pay special attention and refer back to this as you need to. There's a question in the assignment. It's a stretch goal actually, but still. We'll roll the dice, we'll calculate the mean of that particular experiment, and then we will append that into means. Append means place it at the end. So means starts out as an empty list, but one by one we're going to put new means in it, right? And then at the end, we import a special sort of plot called a histogram. And this is another line that you might want to pay special attention to for the assignment. This is how we get to histograms from Matplotlib. And then we say, hey, let's just look at a histogram of the means. And the histogram shows us essentially the count of how many times we see whatever value we're seeing. And it sort of gives you this picture of the distribution. Oh, what does this look like? This doesn't look that compelling. Let's run it again. Yeah, it's kind of blocky. We're only running 10 experiments. Again, we're at a computer. Let's run more means. Let's run 1,000 experiments. And hey, let's make the dice have 100 sides and let's roll it 200 times. Because why not? Ah, all right. And what happens if I run it again? Well, it looks a little different. Maybe I need to increase the numbers, but it's looking much more similar across each run. What is it looking like? Yeah, the Gaussian, the normal, the bell curve, our friend. And this, in a nutshell, is why we care about it. There's other reasons, and there's clearly more math than can be covered right now. But intuitively, it just sort of naturally arises when you look at things repeatedly like this. And what we've really done here is we've empirically verified something called the central limit theorem. So if you're into the mathy stuff, look this up. A full proof is not easy and not necessary, by the way. I mean, it's cool, but you don't have to do it. It's the motivation, though. You want to understand the sort of why we care about this and what the central limit theorem says. And you can see that it's true. You can demonstrate it empirically with just a few lines of code. That's what's cool. What does it say? Well, it says that if you add up and normalize a bunch of independent random variables, such as a bunch of die rolls like we just did, then it tends to become a normal the more you do it. So things just become normal, basically. It's a little bit more fine-grained than that. You have to repeat it a bunch. It has to be independent. These are all independent. Each experiment is like a fair dice, and each time we do it doesn't impact the previous or the next time. It's just an independent experiment. The real world isn't always that nice. But when you have those conditions, things just become normal. And that's really cool. And it's not just for dice. It's even for, remember our friend, the dog sniffing distribution? Yeah, the central limit theorem can work there too. And you can actually get a normal distribution from any old thing and use that for hypothesis testing and other cool topics that we will talk about more in later days and of course in the full course. But any questions on this? This is one of the coolest results of statistics, so I'll leave it up just to stare at it for a moment. All right. Well, I'm pretty much on schedule. Yeah, I'm almost done. This last one I just want to talk about here. So you've learned about random variables, which is like the elemental unit of statistics, the thing we're talking about. And we've learned about sampling. Sampling, we're about to learn. We've learned about distributions, which is how we sort of characterize it. Think of it like the family that a random variable comes from is its distribution. So now we need to learn about sampling. This takes us back to what I said at the beginning. Why do we care about statistics in the real sense? Why is it this not just a math field, but something that data scientists, and indeed all scientists, need to know about? Well, it's because we can't collect all the data. There's a population out there, and what we actually get when we want to say something is a sample. We get to pick some of these and then do our statistics on the sample, calculate the mean, calculate the median, whatever makes sense. More stuff you'll learn about soon. And then whatever we do, we want to then go back and say, hey, we learned this and we think it's true about the whole population, right? Not just about our sample. And how does that work? Well, what's the right way to build this group? Let's say you're a drug company and you have a headache drug, and it's not realistic to collect data on everyone who's ever had a headache, say. So you decide, hey, we'll just ask our employees to try it, right? We'll just give them a few free samples and ask them for feedback. Does that have any problems? Mm-hmm. Ethics, yes, I like that answer. You're right. There's a lot of problems there. Well, even ignoring the fact that exactly there's even before we get to the business concerns here and how you're treating your employees, and sure, the fact that they might not even have headaches, the fact that their incentives might be to not tell you the truth. Who knows? It's just not representative sample. It's not randomly selected. Right? A good sample is random, is randomly and specific. There's a term for it. So, hey, remember our random module? Hey, it's got something called sample. And this does good sampling. You feed it a population and you say, I'd like K things from it. And it picks those K things out and gives them to you. Let's take a look. Let's say our population is just the numbers from 0 to 99. That's what range 100 gives us. Starts at 0, stops before 100. And let's pick 10 numbers at random from it. There we go. We actually got the number 1. Remember though, this list started with 0. Let's run it again. All right, yeah, we get 10 other numbers, and this is a random sample, and this is a true, good random sample. And we got 0 this time. And it's a sample, and we gave it how many things we wanted to collect out of the total population. In general, a sampling process is good if your collected observations are independent and identically distributed. So this is what the statisticians will talk about. This is the property called IID. You can click through and read the Wikipedia article if you want the math. But the intuition is fairly straightforward. And basically, what does the first I mean? Well, independent. The likelihood of any particular observation being in your sample isn't influenced by any other observation. That's important, and that's pretty clearly not the case in the drug company example. And also this one isn't the case, identically distributed. All observations are generated by the same underlying probability distribution. And all observations, I should say, in your sample as the population, right? So they are generated by the same probability distribution as the whole population you're trying to talk about. That's the big one the drug company thing messes up, because what generates it is the being employed at a drug company, and that's different than being a whole population. Now, you may be wondering, how big does my sample need to be? It's a good question, and another question for the future. But hypothesis testing, which we'll learn more about, we'll touch on that some. So I made it in an hour. This is just an introduction. There's a lot more to know, that is, about statistics. It's worth going fairly deep on this. You don't have to write proofs or get a PhD, but I encourage you to dig into some of these resources. And I leave you with a little joke here. Granted, we didn't talk about correlation, so this is a joke that will get funnier as you study more. Any questions? And thank you all for your participation. Sure. Yes. Correlation does not equal causation, exactly. Though it can suggest it, right? In any case, this link here is the assignment notebook. And things are going to start coming together. To do this assignment, you're going to want to remember things from the first 2 days as well. You're going to want to load data from a data set. It's a CSV. You're going to want to use pandas. And then you're going to want to explore the data and summarize it. And you can you can use built-in functions in Pandas and otherwise to calculate these things, but please also, for the specific questions and for just a few variables, try to calculate it yourself. Calculate the mean, calculate the median. And for a discrete variable, calculate the mode. And do that, take a look, and then, for fun, you can simulate more data, and as an optional stretch goal, you can simulate a lot of data, run your own Monte Carlo. So that's the assignment. Please take a look, and please follow the 20-minute rule. Ask questions. You can use the question emoji in Slack, and that lets us know that you're asking a question and you'd like some help, and somebody will help you. So that's it. Any questions before we break? That's a good point. Yes. So all this randomness, I didn't set a seed. That's on purpose because I wanted to show you that it was really changing. But the seed is a way to refer to the fact that if you specify a sort of special number at the beginning, you always get the same random draws. Don't worry about that right now. There are situations where that matters. That doesn't matter right now. The 20-minute rule is if you are stuck for 20 minutes, ask a question, right? Your time is valuable and we want you to succeed. And yes, it's not the 0-minute rule, right? You should struggle some. This is not stuff that is meant to happen for free. It's hard for everybody to learn this. But if you're struggling for 20 minutes, you should ask for help. And that's a good note to end on. So thank you, everybody. An hour to work on this, and then an hour to meet with PMs. And then, of course, at the end of the day, please fill out your stand-up form. Make sure you make a copy of this to work on, and make sure once you make that copy, you share, and you make sure it says anyone with the link can view. And then this link is what you want to put in your stand-up form. All right. Thanks, everybody. I'll have the video up shortly.